So this is from our revision solutions. This is De Moivre's theorem, and I want to prove that sine 3 theta equals 3 sine theta minus 4 sine cubed theta. So the first thing that I need to do is I need to set up a complex number in polar form. And it's only a very generic version that I'm going to use, and I'm going to be able to use the modulus being 1, which I effectively then get to ignore. So really I'm working off cos theta plus I sine theta. And then I want to have a look at my question and I want to identify what power I need to put this complex number to. So when I look through this, I see an awful lot of 3's, and I got a sine cubed. Okay, it's going to be a power of 3. So I know there's a 4 in there as well, but it's totally overpowered by the 3's. So let's go for that. So I'm going to say z cubed equals cos theta plus I sine theta cubed. And then I want to use two methods to apply this cubing. I want to first of all use De Moivre's theorem. So I want to just fill in that power in front of my angles, but I also want to expand this complex number using binomial expansion. So I have to do it both ways and then equate. De Moivre is the faster of those. Let's do that first. And of course that just lets me slot that power in front of theta. Then I'm going to do the binomial expansion. So I've set up my binomial expansion with my n choose r's and my various different powers on cos theta and I sine theta. And then I want to tidy this up. And so that's each of the individual terms tidied up. And now I'm going to look at this overall, along with the De Moivre version of the expansion. By the way, I've skipped a couple of steps here to get as far as this final expansion. So if you need to take a few more steps to get there, that's totally fine. Don't forget, of course, that I squared is minus 1 and I cubed is minus 1i. That explains my minuses in these two positions here. And I'm going back now to look at the original question, and I'm going to compare it with these two different statements that I have here. And I see in my original that I'm looking for sine 3 theta. Okay, so sine 3 theta is this part of my De Moivre. You can see that it's the imaginary part of it. So what this question is asking me to do is focus in on the imaginary components of my two expansions. So I'm just going to take these underlined parts of my statements and make an equation from them. So I'm going to be able to say, well, this expansion is equal to this expansion. So I sine 3 theta equals to these two parts that I've underlined here in orange. And when I actually equate them, I can ditch the I because they all have I. So the equation is going to look like this. Now, it's not quite the way I want it to look. I mean, it's got kind of aspects of what I'm aiming for, but I'm not quite there yet. I've got sine 3 theta. I've got a 3. I want only to have sine theta. And I should have 4 sine cubed theta. So something else has to happen yet. And I notice that I've got this cos squared theta, and I don't really want to have a cos squared theta. So I'm going to have to get rid of that. And of course, I can do that by referring to my log tables. And I'm looking here at page 13. And I notice on page 13 that I've got this really useful rule, cos squared plus sine squared equals to 1. So that means I can replace my cos squared in that equation. So before I do it, I'm just going to note what it is that I'm going to substitute in, and then I'll fill that in to the cos squared position in the equation. I feel like this is a tiny amount of space. I think actually in real life you'd have more room to complete this question. Anyway, multiplying this out, just watch as I'm doing this. I've got the 3 out front. I've got the 1 minus sine squared theta. I've got the sine at the end. So it's 3 by 1 by sine theta, giving me 3 sine theta. That's promising because I'm on track for this guy now. Minus 3 sine cubed theta. So that was 3 by minus sine squared theta by sine theta, giving me this guy. And then I have that last guy at the end, minus 1 sine cubed theta. And then it's simply a question, just putting those last two terms together. A nice little QED at the end is a little pat on the back to myself for getting the right solution. Job done.